So you are probably, well, not climate researchers, but you are going to use climate model data sooner or later, for worse or for the better. So I think it will be good for you to have an idea how climate models work. What are the limitations? I'm going to talk mostly about the limitations of climate models, because the success, we hear from the successes almost every day, but very little of the limitations. And for you that are going to use the climate model data at some point, it will be useful and interesting to see what are the limits of those data, at least of current climate models. And as I said, we are going to be quite critical with climate models. And that's the reason why I want to start the presentation with two quotes by Stephen Schneider. Stephen Schneider was, unfortunately, he passed away, I think 5 years ago. Oh yeah, okay. Exactly, 5 years ago. And he was involved very early in the IPCC reports and was the editor of Climatic Change, this very well-known journal on climatology and physics of climate, and also climate impacts. So by this I mean that he was not a skeptic at all, but he was actually very much involved in the dialogue with climate skeptics. So he tried to convince them that actually climate change is a very important issue, that climate change may be happening already, I mean anthropogenic climate change. But his attitude was actually quite a, fostering dialogue among all the participants. And what I wanted to quote two sentences that he wrote quite a long time ago. He said that warming is unequivocal, and so there is no question about it. We see a warming. But there is another question which actually is more interesting than that the bold statement that warming is occurring, is how much warming will occur in the future. And these are much more complicated, much more complex question. To answer that, we only have one tool, basically, and this tool is climate models. And he also said we don't need, or we should avoid to be too arrogant with climate models, and that's what we are going to do in this talk, to look at the critical and problematic, well, a few of them, aspects of present climate models. However, that is very important for you to notice. That doesn't mean at all that anthropogenic climate change cannot be a problem. Because actually the global warming was already predicted very long time ago, much longer than the advent of climate models. And it was predicted almost, well, longer than 100 years ago by Arrhenius. And he realized that the increase of CO2, which is a greenhouse gas, and we will explain a little bit later the basics of the greenhouse effect, must lead to surface warming. There is no escape to that conclusion. It is as sure as if I said here, I'm turning the heating up in this room with nothing else changed, so the windows remain closed and the doorways remain closed, the temperature will go up. And with that level of security, I can say that if CO2 gas concentrations go up in the atmosphere, the warming at the surface has to go up. That's for sure. But I said a very important sentence: if anything else, everything else remains unchanged. If we increase the CO2 concentrations by about 300 ppm, by the way, which is the current concentration in the atmosphere of CO2? Yeah, very good, okay. And the pre-industrial value, so before the industrialization?
200.
Now? 280. Okay, but it was very close. If we double this concentration, this action will lead, if everything else remains unchanged, will lead to a warming of 1 degree, which actually is a very small warming. It's very moderate. The problem is that this initial warming kicks or triggers changes in the system. As I said, if everything else remains unchanged, the warming will be about 1 degree, but this warming triggers changes in the cloud cover, changes in the currents in the atmosphere, in the currents in the ocean, and that may lead to accelerated warming, so to reinforce the warming, or to moderate that warming. And this is called the feedbacks. For instance, I will mention just two important feedbacks that will be very easy to understand for you. When the surface warms, so we have more evaporation. So we have an increase in water vapor in the atmosphere, which is a very strong greenhouse gas, much stronger than CO2, and that will reinforce the initial warming. On the other hand, cloud cover may change, and clouds reflect sunlight, so that they could possibly moderate the initial warming. And this is exactly the problem. What will be the effect of those feedbacks, to calculate them with climate models? And this is a very complex question. So that's the reason, we will see later, why some models predict, under the same conditions of increase of CO2, predict a warming of, let's say, 2 degrees, and some of them go up to 6 degrees. So we have a range of 4 degrees in the global increase of global mean temperature. Calculated by two different models, but under the same physical assumptions. So all the models are trying to replicate the climate as it is. Why is that? Well, we will see it later. Some of the reasons. Why is this? But first, we'll revisit this figure. It's a very important figure that probably Eric Shellstrom showed as well. Is the energy balance of the Earth. So you see, this is a quite complex figure, but there are some guidelines here. So we have here yellow color, which is the energy coming into the system, and the red color is the energy out of the system. Actually, the Earth is not, well, the amount of energy that is stored in the Earth doesn't change that much. It's like a lake. You can assume this is a lake, and this is water flowing in and water flowing out. And we have here a reservoir. So what is the water flowing in, the energy flowing in? Of course, everything comes from the sun. And this water, you can imagine that it's rivers that are diverted before they reach the lake. Well, some of them is reflected by the clouds, as we'll see. Some of the energy, some of the water reached the lake, and then they have to leave the lake, and they have two possibilities. One is by evaporation. So the energy, when the water evaporates from the surface, that takes up energy. This water then rains somehow, somewhere, and that releases the energy higher up in the atmosphere. And then the second way in which the energy leaves the system is by infrared radiation. You know that every object that has a temperature, for instance ourselves, are emitting infrared energy all the time. That can be seen by an infrared camera. We cannot see it, but the energy is there. And in the end, this is the way in which the energy leaves the system. Now, imagine that this is really a lake, and this is water flowing in and water flowing out. Now suddenly we have a flooding, so we have more water, rainwater that goes to the river. What happens here in the first stage? So the water level in the lake rises. So that increases the pressure, and the water flow here increases again until the same amount of water that comes in comes out. But the difference is that the water level in the lake has increased. So if we increase the solar energy, in the end we have a transient phase in which the temperature has increased until enough energy leaves the system to compensate the increase, the initial increase in energy, right? In other words, if the sun gets stronger, the temperature at the surface will increase. That's for sure. Everyone believes that. Well, the same effect is if we close here the window in which the water or the energy is flowing out. And this is the greenhouse effect. So the energy is leaving, the infrared radiation is leaving the system. When we increase the CO2 concentration, what we are doing actually is closing the valve, closing the outlet of the system, so that the water is retained here The level of the water raises until the pressure goes up, and then enough water can leave out again. So in the end, the same amount of energy is flowing in as flowing out, but the energy level, the water level, has increased. So it's the same mechanism, a little bit different if we increase the energy here or we close the window here, but the temperature has to raise in both situations. So how much? When we increase the concentration of CO2 in the atmosphere, we close this window by 4 units, let's say. And actually, the window, which is open usually, is, you see the numbers here, 240. The energy that's coming out is 340 watts per square meter. But the point that I'm making here is that when we close that window by the greenhouse effect, it's a very small number compared to all these numbers that we see here. Nevertheless, that small number leads to 1 degree warming by itself. Now, if additionally here the clouds are changing so that all these energy flows change as well, and some more energy is reflected or less energy is reflected, then that changes the whole system. You see, that's a very complicated system that can change, and that theoretical warming of 1 degree can go to up to 4-5 degrees, right? Now we start criticizing a little bit climate models. How good are climate models able to replicate the observed energy balance? We are not talking about any climate change now. We are talking about the present situation. And this is the observation. So this is the amount of energy flowing in, as I said, 340 watts per square meter. With this part is reflected. This is the infrared radiation going out. This is at the top of the atmosphere. This is the surface. And here we have also some numbers of the energy balance at the surface. As I said, these are the observations, and here we have some range which is produced by current climate models. For instance, let's look at the outgoing long wave radiation, the infrared radiation. We have an observations of 240, and we have a range, simulated range, between 230 and 245. So we have a range of 12 watts per square meter. Some models go to 230, some models go to 245. We were talking that CO2 forcing is about 4. So the uncertainty that we have here in all the range of climate models is 3 times as much. So we can imagine here that the models may have a problem simulating just the present state of the observed climate, let alone simulating climate change. And do you have a question? You are looking a little bit. Is everything clear?
Clear.
Yeah? Really?
Just is scared and so much uncertainty.
Well, probably you will be a little bit more scared later. Now when we are comparing climate models and observations, that we will do in this talk and also later in the paleoclimate talk, we have to be aware that there are 2 sources of climate variability. One is the forced climate variations and the unforced climate variations. What are the forced climate variations? That's just a definition. It is the climate variability that is caused by external factors, and I will just list them, and then later in the talk we'll understand better what they are. For instance, one external factor is the solar irradiance, so the solar energy. It doesn't belong to the climate system itself, it's just a given parameter. And when I'm trying to simulate the climate, this is a number that I can put into the model. The model cannot choose that number. It's just an external driver. I'm driving the model with that number that I choose. Another forcing is the greenhouse gas concentration. This is also, in most models, a number that I put voluntarily into the model. The model cannot change that. That's why it's an external, it's a force driver, external forcing. What are the unforced variations? We have seen them a little bit in the previous talks. They are also denoted internal, random, or stochastic variations. And you can think of them like, well, the weather today was different as yesterday, right? And why? Why is it different?
Clouds.
Yeah, well, we have clouds, but the sun was the same as yesterday at the top of the atmosphere. The greenhouse gas concentrations were the same as yesterday, but the temperature can be really different from yesterday, and tomorrow will be different. And if we are here next year in the next summer school, the weather will be also different. And if we calculate the mean temperature this year and the mean temperature next year, they will not be equal, although both external forcing factors, the sun and greenhouse gases, will be basically the same. So there are some variations that are not controlled by the external forcing, that they are random, that they are somehow unpredictable, and well, you can think of them that these random internally generated variations are present in all complex systems. Imagine that you may have a sister, for instance, a twin sister. I don't know, but let's imagine that. And you have grown up together, same family, the same environment, the same country. So probably you have the same level of education. So your life history will be similar, but not the same. For instance, in school, your sister may have a very good history teacher, and you may have a very good physics teacher. So that your sister decides to study history, and you decide to study mathematics or whatever. So your life histories will start to get out of sync, although the external forcing, the external conditions will be the same. So there are random events in your life that you cannot predict, that you cannot control, and that causes an asynchrony then in the time evolution of your life. We can also imagine that we have two Earths in the solar system. It's the same history. They are forced by the sun in the same way, so the external forcings will be equal, but in one of the Earths, for instance, life appeared 100 million years later, just by chance. The appearance of life probably is a random event, so that the history of these Earths in the solar system will be now different. Statistically seen, they will be very similar from outside, but if we look at the time evolution of these both Earths, they will be different. So these are the internal variations. And one example that probably is very well known to all of you is ENSO. It's the El Niño Southern Oscillation. It's a phenomenon, a climate variability phenomenon, that is, as we will see later, is caused by the interaction between ocean and the atmosphere and cannot be predicted. We cannot say if there will be an ENSO in 5 years' time. We can say that temperature, the global temperature, will go up if we increase, for instance, solar radiation of greenhouse gases, but we cannot predict if there will be an ENSO phenomenon in 10 years or 5 years. Statistically, it will occur every, let's say, 5 years or so, but we cannot really predict the timing. So we have to consider that we have these two sources of climate variability. The problem is that we know that we have this variability, internal variability at annual timescales. We may have it also at decadal timescales, so not every decade is the same, even given that the external forcing is unchanged. So the 90s will be different as the 80s, and will be different at this decade. Will be the same with centuries. Imagine that we have a constant sun, a constant greenhouse gases. Will one century will be the same as the other century? Well, probably not. But this is a much more tricky question, because we really don't know what are the main phenomena that will contribute to make those centuries different. So probably there will be small trends in the temperature in the centuries that are different. And now we can ask ourselves, the trend that we are seeing in the 20th century, is it caused by changes in external forcing? Or is it caused by these random variations? And this is the important problem of, well, detection and attribution of climate change. We have to distinguish between the climate changes caused by changes in the external forcing and climate changes that are internally generated. And this is actually a tricky problem, a difficult problem, and one that hampers, well, the detection of any climate change, and also the estimation of future climate change, as we will see as well. Okay, let's have a short look now at the structure of climate models, and after this slide I will show you a movie, but I see that you're actually already quite bored and sleeping. You have seen this slide before, right? But the main message is that, well, a climate model is a computer game, like the ones that you can buy at the shop, that tries to simulate the climate, well, the Earth's climate. And the philosophy is as follows. So the Earth is divided in grid cells, not only in the two-dimensional surface, but also in the height and depth, so in the atmosphere and in the ocean. These grid cells have a size of about, let's say, currently 200 kilometers, right? And, well, let's say here 200 meters in height. Now imagine that you are a climate model, all of us. Each one is a grid cell. So each one represents the climate over a grid cell that is 200 kilometers wide and 100 meter height. I give you at the beginning values of the temperature, of the wind, of the humidity, of solar radiation, and so on, right? And well, each of us then keeps that number. For instance, you are the grid cell that represents the Baltic proper at the surface. So you are representing the whole Baltic proper, 200 kilometers wide. And you have only one value of temperature and one value of wind for the two components and one value of humidity in the atmosphere. Every one of us then has these values, and then we wait 30 minutes. I'm the referee, and then after 30 minutes I blow a whistle, and you calculate, you communicate with your neighbor, say how much temperature do you have, how much temperature do you have. Well, these two guys are warmer than I am, so I'm going to get energy from them when at the blow of the whistle. And the same with humidity. I'm comparing how much humidity do you have, and you have, well, you have less, I'm going to give you humidity. And then I blow the whistle and you make this exchange between your neighbors, only your neighbors, right? And at some point we'll say, well, the guy on the right and on the left has given me too much humidity. I cannot hold that amount of humidity. I have to get rid of that. And one possibility is that you go to the bathroom, and the other possibility is that you produce rain. And that's how the models actually produce, well, rain. All these rules that exchange the energy and the humidity and the momentum are based, of course, in the physical principles, the Navier-Stokes equations, but they are only based on that. They are not the physical laws. They copy them somehow. So they are approximations. And now I wanted to illustrate this, I want to show you this little film. Let's see if I can find it. I cannot read it. No, this is not this one. So this film is basically what I've told you, but in a more nicer way, in a nicer way. So this shows go forward, the French model from the Pierre Simon Laplace in Paris. Is there anyone from France here?
But not Paris.
Where are you from? Oh. From?
Nantes.
Oh, okay. I've never been there. So, well, this is the basic idea. The Earth is divided in grid cells. And as I said, each grid cell will try to simulate the local, well, actually it's not local climate, it's something like more regional climate. And all these rules that drive the exchange of energy and momentum try to reproduce the physical equations. Now, the most sophisticated models also try to replicate vegetation and the biogeochemical cycles, for instance, CO2 and methane. So they are really complicated. We put some greenhouse emissions so that we can increase the CO2 concentration in the atmosphere. In the ocean, we have also salinity. So the ocean grid cells will also have a variable for salinity and for currents. There will be convection. If the grid cell above me contains water that is heavier than myself, it will give me water. Okay, what am I going to show now? David, are you here? So this fed on a very complicated computer, of course. Well, these are really very expensive computers. We were talking the other day that the computer that will be bought in Hamburg for climate simulations will cost 40 million euros, only dedicated for climate simulations. So you could fund very, very many PhD students with that. But of course, the PhD students are not so quick as simulating the climate. Although I should say that, well, when the film is finished, I will comment. Okay, you can see here how the model simulates clouds. We'll look later how the skill is in simulating clouds. So this is the sea surface temperature, also simulated by the model, and well, the winds and so on. So you can see that models tend or want to be really complex, and they are able to produce a very large amount of numbers. Whether or not these numbers are reasonable, that's another thing, but they are able to produce a huge amount of numbers, and they're the ones that you will use. For instance, if you in the future in your PhD want to use well, to predict climate impact on some ecosystems, you will certainly find a climate modeling group giving you data for the winter temperature in well, I don't know, in Russia in 2080. No problem. The question is how reliable those numbers are. Okay, now we go a little bit further into the problems of climate models. And one of the problems is the resolution, so the size of those grid cells. As we mentioned before, one grid cell in a typical climate model today will represent the Baltic proper, or 200 kilometers, so that for the Baltic we will have probably, I don't know, 9 grid cells, so 9 people. For Germany, well, probably 5 or something like that. Spain will be about 5. So very, very little information. But you can look at the evolution of this resolution through history of climate modeling. So this is the first assessment report in the 90s, and the horizontal resolution was about 500, and that was Europe as seen by a climate model at that time. So you see the Baltic was closed, the Mediterranean was closed. Well, Spain is here. You cannot recognize France, you know, that France didn't exist. And the United Kingdom didn't exist either. Sweden, well, it's... Now we go into the future. These are current climate models. You see that they look much better, although we have a resolution still of 100 kilometers. So we have to decide if the Baltic will be open or closed. If we decide, okay, we will leave the Baltic Sea open, then the opening, the outlet to the North Sea, will have to have 100 kilometers wide width instead of 15, yeah, right? Or 10. I don't know, how much is it in reality? The connection to the North Sea?
3 kilometers.
3? Okay. Well.
4.
Yeah. On the other hand, if we decide we leave the Baltic Sea closed, because 100 kilometers will be too unrealistic, well, then it is closed. There is no exchange of water. So this is one of the main problems that leads to further problems, that, as we will see later. Nevertheless, if we look at the global scales. The global climate models want to simulate the global climate. They look really very realistic. This is the surface temperature simulated by a climate model, and this is the annual precipitation. For instance, we look at the temperature, we see actually, well, of course, a meridional, so the north-south gradient of temperature, diminishing towards the poles. But if we look into detail, for instance, we can see here these sloping up isolines of temperature caused by the Gulf Stream. So the climate model is able to reproduce the Gulf Stream and the Kuroshio as well. And we have here the warm pool over the ocean continent in Indonesia. And we have also some hints of upwelling, not here but here, for instance, as well. So the climate models are not that bad at these scales. And if we look at precipitation, well, that looks really realistic. So we have the Sahara where there's no rain. We have very, very large rain in the rainforest here in Southeast Asia. The minimum here in the Eastern Pacific, and so on. So at these scales, they are really, well, not bad. They look actually quite good. But we encounter one problem. We have a temperature range, I mean in the mean now, of 100 degrees between the equator and the poles, right? And we are trying to simulate a change of 2 to 3 degrees. So we're actually requiring for a climate model, imagine that I put here 2 degrees. I add to this figure 2 degrees. You wouldn't see a difference at all. I mean, the color coding goes 10 degrees step. You wouldn't see it. Nevertheless, a warming of 2 degrees globally is considered to be already dangerous, maybe. And if you think about, let's say, the temperature, mean annual temperature difference between Stockholm and Paris, which are very different, right? It's about 5 degrees. The temperature difference between Madrid and Cairo, which are very different climates, is 5 degrees. So a global warming of 5 degrees is a catastrophe, really. It will change the way we live completely. So I can believe that 2 degrees warming can be dangerous, can become dangerous. I am not a climate impact expert. I have no idea about ecology, but I can believe that 2 degrees is really becoming very dangerous. But the amount of accuracy that we are requiring from climate models is much too high. Climate models, in my opinion, nowadays are not able to have that degree of accuracy, right? Well, we have now many climate models. So each climate modeling group wants to have their climate model. So I saw before the climate model from the French group in Paris, but we have about 55 climate models globally. They are all different. So the structure in which this computer game is written is quite different, but they all aim to reproduce the same reality. And well, we encounter the first philosophical problem here. We try to construct a physical theory to describe observations, to predict climate change, but actually we have 55 theories of that. A scientist would say, well, 54 are wrong. At least, well, at most, one is right. So we have to get rid of 54 theories. A climate impact person or a policymaker would be interested to say, no, actually, I like to have all of them because I have to know what is the uncertainty in the projections. So we have two different points of view. So the scientist working in the ivory tower that says most of those theories are wrong, and I want to find the very good, perfect and correct climate model. The policymaker is interested in the other, exactly in the opposite. He really would like to know what is the range of projections so that he can or she can take better decisions, hopefully.
I would
Okay.
The policymaker is the one that wants the one number so that he can make policy with that. And then the scientist is the one who's saying like, yeah, well,
no. No, I don't agree. I don't agree with that. I mean that perhaps you are already contaminated by the modern way of thinking. The traditional scientist would say, I want to know what is the correct theory that better describes reality. That's what, let's say, the scientists in the early 20th century or the 19th century wanted to know. This now fashion of producing a lot of theories, and Monday apply one and Tuesday apply the second one. Well, it's new. It's a new fashion, but it's not a traditional scientist approach. And the policymaker would, of course, would like to know one number. If you can tell her this is the correct number. Of course, there is no uncertainty there. Of course, that would be the optimal situation, but that's not possible in climate. Well, now we have these 55 theories of climate change, and we try to predict the future, all based in the same physical principles. And we see, for instance, that we drive all these models with the same concentrations of greenhouse gases into the future. This is one scenario, the representative concentrations path of CO2 concentrations in the future. And I get a range of warming between 3 degrees and 12 degrees. 3 degrees and 12 degrees. So this is a range of 8, right? Well, this is not acceptable, of course. From the physical, or for a traditional scientist, this is not acceptable. Even if we go to other scenarios, so a more optimistic, so a mid-range increase in CO2 concentrations, we have a range of 2 degrees. If we accept that 2 degrees make a difference between no danger and a dangerous climate change, I mean, this is also not acceptable. Why is this? Why the climate models that are based in these very same physical principles can be so divergent? Well, and so divergent not only in the range, but also in the sign of predictions. I show you here one example, a real example, that we did for one charity, one NGO that was operating in Namibia. And actually it was a very good organization. And they wanted to plan for adaptation of climate change in Namibia. And one of the problems there, of course, is the scarcity of water. And they asked another very well-known NGO, his name is Greenpeace, and of course they told them it's going to get very, very dry there. So you have really to adapt very, very quickly. So they were a little bit, okay, let's check that, as you have to do always in science. And they asked a group of climate modelers, what are the models telling us about future changes in precipitation in Namibia? And this is the temperature, and this is the precipitation. Of course, the temperature gives you, let's say, all the models agree in some sense. It will be warmer, although the range is between, again, 2 degrees and almost 5. So a very large uncertainty. But nevertheless, you can say, okay, it's going to get warmer. They agree in that point. But now look at precipitation. If this is the model that is right in the end, it will really get very, very dry. If this is the model that in the end is right, it will be a little bit wetter. So really you cannot, the models are telling you that will be very difficult to plan for adaptation there. The information today is not enough to plan adaptation. We have to adapt to both scenarios, wetter and drier. So that's an illustration that sometimes, you have to look at what climate models are telling us. And this story is similar, for instance, to what happens with hurricanes. If I ask you what will happen with hurricanes in the future, probably most of you will tell me, well, we'll get more hurricanes due to climate change, because that's what Al Gore said. And we all witnessed what happened with Katrina. and so on. Actually, what climate models are saying, if they are right, is that hurricanes will not change. And if they change, they will get less frequent. That's what climate models are saying. So you also have to be, in your impact studies, be careful what you read, what are the sources that you're taking, and well, what the climate models really are doing. There are, in climate impact studies, of course, climate projections, and some of them get really bad, but not all of them, and you have to be careful about that. Well, what is the main source of uncertainty? Why all these models produce different results? This is a real picture. This is not made up. And this is the answer, or one of the answers. We saw that the resolution of climate models is about something like 250 kilometers. Now, if I look out of the window and I try to describe what is the cloudiness in the whole, let's say, Baltic area by one number only, that will be very difficult. I can see, of course, now very different types of clouds. Not the cloud cover is homogeneous. So there's a very, very rich structure in the cloud cover. But the models cannot reproduce that. They can only have one average number for cloud cover for that grid cell. So what they do? Well, they try to come up with a solution. Actually, it's an approximate solution. It is called a parameterization. So a typical climate model would say, my humidity in my grid cell is, relative humidity is 70%. I have wind coming from my neighbors, so I have to produce some convection in my grid cell and some rain. These are all average values. And then I have a simple formula and I calculate, okay, my grid cell will be covered 60% by clouds. So that will be what the French group will say. Now the German group in the model will say, no, my formula gives me 40% cloud cover. And the American group say 50% cloud cover. Now, if yesterday I was lying in the sun after the sauna, and it was really a very different temperature when a cloud came and blocked the sun, or when it was sunny. I could feel it really differently. And the climate model will also see it. The cloud changes the amount of solar radiation very, very much. And that's one of the main differences between climate models. We can see it here in the next, in the next slide. Yeah. Here we have a collection of different climate models. This is the warming simulated by each climate model after doubling the CO2 concentration. This is the climate model that produced less warming, about almost 2 degrees. And this is the model, one of the models that produced a very strong warming, almost 5 degrees. What is the difference? Here is the simulated change in cloud cover by both models. This model is telling me that cloud cover will increase, so that more sunlight will be reflected back to space. That's why the warming is reduced. This other model is telling me that cloud cover will be reduced, will have less clouds. So the solar radiation will be increased at the surface and it produces more warming. So what is the message here? We cannot even say how cloud cover will change in the future. Some models is producing more cloud cover, other models producing less cloud cover. Even the sign is different. And then in between you have, quite a lot of range, which is to a very large extent explained by the different simulations of cloud cover. And this simulation of cloud cover is not based actually, it's not totally based on physical principles. As I explained, it's really an approximation to be able to produce a number of cloud cover on a grid cell that is 200 kilometers wide. You cannot say, okay, this model is wrong because it's not based on the real physics. No, all of them are trying to replicate the real physics. But when you go at very, very small spatial scales within the grid cell, you have to well, do some guesswork, and then it's where the difference comes in. So very critical predictions of climate models are based on not so well-founded principles. You could hear that climate models are based on physics, and that is to some extent true, but not completely true. And that they are not based on physical principles on very important issues. Should we make a break now, or are you tired? Yeah, I think, yeah? Oh. Okay. Well, of course, you may interrupt me anytime. You know? If you feel sleepy and have any question, just interrupt me. Because it's really more important to, now you have the chance to know everything you wanted to know about climate models. It's your chance in a lifetime. I don't think that many climate modelers would be so willing to answer honestly. Okay, now we're going to try to answer this question. Can climate models simulate the observed climate before we go into climate change? And well, we already saw at the beginning that they have problems in simulating the basic energy balance. So it's quite reasonable to think that they will have a problem simulating the real climate. This is a figure that we saw really very, very often. I think this is taken for the IPCC report. And this is a comparison between the observed temperatures, which is the black line, in the 20th century, and climate simulations. Now here there is a trick, because they are not the simulated or the observed temperatures. They are all deviations from a mean, and this mean is different. So in other words, all the models have been realigned to have zero mean. This curve shows deviations from that reference level. And so you could say, okay, yeah, the models actually are quite good in reproducing the observed temperature, right? But now let's look at what the models actually simulate without this artificial alignment. And this is the figure. So these are, again, the black line are the observed temperatures. So the mean, the global annual mean temperature is, well, roughly about 40 degrees. And this is the range of model simulations. So we see that there are some models that go to, well, 15, some models 12 degrees. So we have a range of almost 2.5 to 3 degrees in the simulation of the annual global mean observed temperature, which is the easiest possible variable to simulate. Again, if we think that dangerous climate change will be 2 degrees warming, we see that in the ensemble of all the models that we have, we don't have that precision. Some models already are telling you that we have dangerous climate change today, right? So the argument that is normally made is, okay, what we are trying to simulate is climate change, not the absolute climate. So I'm going just to see how this model warms in the future, reference to their own simulated climate. And this is, well, defensible in some sense, but not in very important senses as well. For instance, this model, that is very cool, very cold model, will have a very extensive sea ice extent, because it's global, is actually, well, very cold. So the reflected solar radiation from the surface will be artificially high. All the climate in the Arctic will be unrealistic in this model. So when you're going to simulate climate change with this model in particular, well, you can say, well, this is not going to work. I mean, the model will produce some warming, of course, they produce something, but this is not going to work if we start with a sea ice cover that goes, let's say, into the mid-Atlantic. The same can be said with this model, with a very, very reduced ice cover. That the heat transfer into the ocean will be artificially high and unrealistic. And so the climate change simulated by this model would be suspicious as well. For climate impact studies, this is even more important, Because for climate impact, for instance, I think for plants, for these little animals that cause zooplankton and so on, the absolute level of temperature is important, not the temperature change. Well, temperature change is important, but it's not the same if you start to 20 degrees and go up to 22, or you start from 15 and go to 17, right? I think for the biological cycles, for the tourists in Spain, for instance, it's very different. So I can imagine that for phytoplankton and zooplankton it's the same. For climate impact studies, it's very important that you look at the absolute temperatures. So there are some tricks again. You can correct the absolute temperature to the observed level again, but you cannot be sure that the climate change simulated by that model for your impact study will be realistic. So you have to be really, really careful in this point for climate impact studies using climate model data. Now let's look again at the difference between the mean temperature simulated by the models and the observations, but especially resolved. So not only global mean. These are the observations, so from the Helmholtz-Zentrum, and this is the difference between the simulated temperature by each model and the observations. So these are already differences. And the most important point in this slide is that I need a range of -5 degrees to 5 degrees. This is already a very, very wide range. Some models are getting the temperature of Antarctica 5 degrees too warm already in the present climate. The GFDL model, which is one of the best, from the what is the name of GFDL? Well, it's an institute in New York. I cannot come up with the name now. The Geophysical Fluid Dynamics Laboratory. This is one of the best institutes, the climate research institutes in the world. And their model is too cold over Europe, Russia, Western North America by about 4 degrees. So if this climate would be the real climate, it will be really cold here in Scandinavia. Really, really cold. So models actually, some models produce a quite unrealistic present climate already. And then the question is, can we rely on them to simulate climate change? Well, depends on what you are interested. But we again be very, very careful. The same for precipitation. This is the difference between, well, this is the observed precipitation, right? And this is the differences between models and the observed precipitation. And again, the range is to 150 millimeters per year to minus 150. That's wrong. There's millimeters, not centimeters. The mean rate of precipitation globally average is 1,000 millimeters per year. So we have differences of the order of 10-15% in the observed rate of precipitation. Okay, let's go now into trying to test climate models now in simulating climate change, not the present climate, but the trends, the climate change. And we have again here the observed temperature, two different data sets, but they gave basically the same result from the Helmholtz-Zentrum and from the Geesthacht in the US. This is the global mean annual temperature, and this is the range simulated by our 55 climate models in the historical period. So this should reproduce the range of observations, and these are the scenarios. In this case, the scenario is the middle scenario, 4.5. Something not very pessimistic, not very optimistic. And now we see here perhaps a hint of disagreement. That is the so-called hiatus in the resting temperature. Right? You probably have heard about it, that no? Well, it's all over the place. Okay, perhaps you have heard that since 1998, something like that, the degree of warming that has been observed here is almost flat. So you have here very strong warming in the 90s, and then here warming has stopped, in some sense, has stopped. Actually, the trend here is about 0.05 degrees per decade, and here is 4 times as big. So this is actually very well within the range of trends simulated by models. If you extrapolate here, well, you actually go in the middle of the models. They have been aligned here to agree, of course, we saw that. But nevertheless, we're trying to see if they can simulate the trends. But if we extrapolate the more recent trend, the last 15 years, we see that, well, there is a hint of disagreement already. On present trends of the last 15 years only, it's a short period to calculate the trend, but let's assume we can. Models and observations will disagree clearly in about 10 years' time. And then if that continues, they would say, okay, the models are really not realistic. If we calculate the trend not with the last 15 years, but the last 25 years, the situation is not that worse. And well, the extrapolated trend will be within the range of models. Now, this is now a very current discussion if the models are running too warm towards the observations. And what was the reason why they agreed here and that they apparently tend to disagree here. Let's have a look at this, the main figure of this paper that was very recently published by the group of, Jochen Marotzki is the director of the Max Planck Institute in Hamburg. And this is a very prominent paper on the hiatus. And the argument, they said, okay, yeah, in the present period, here you have a representation not of the temperature, but of the temperature trends calculated every 15 years. So he took a segment of 15 years in the observations and calculated the trend. You see, in the 20th century, the trend was about, 0.2 degrees per decade, 0.15, something like that. And here they go down to almost 0, as I said. So there is a slowdown of the warming. And this range is what the models actually produced. And he said, well, I mean, this is not a problem. Here we are in the lower range, and actually the observations are almost outside the simulated range. So you could say the models are invalidated here with this observation. But there are other periods in which the observations were actually warming faster than the models. So there is a statistical variability. Some periods the models are warming slower, some periods they are warming faster. That is to be expected. As we discussed before, the models are not reproducing the exact timing of the observations. They are twin Earths, they are parallel worlds. So we have random variability that avoid us or to prevent us to reproduce exactly the annual succession and the decadal succession of temperature. So we have some variability, and in some periods the observations are warming faster, and other periods are warming slower. This is the opinion of these authors, which is very defensible. However, there are other opinions, and I want to show you the other point of view here. This is the histogram of the simulated model trends in this period, at the beginning of the 20th century, in the first third. These are the observations. You see that the models are warming less rapidly than the observations here, right? Here is the recent period, as I said. This line is the observed rate of warming, and all the models are to the right. They are warming faster. Now there is a difference between these two figures, and it's a tricky difference. In this figure, the histogram is centered about 0. That means some models are warming in this period, some models are cooling. So the trends can be positive or negative. That means that the external forcing is very weak, and the internal random variations are much stronger. So these rates of warming are quite likely caused by random variations. And by chance, the observations are here warming faster than the models. Here in this period, all the trends are positive in the models. That means that they are driven very likely by the external forcing, by the increase in CO2 concentrations. And in this period, in which the external forcing is more important, is where the models are running warmer. Right? So this is the other point of view, the critics of this paper. And that would be a conclusion that, okay, the internal variations by the models are roughly well reproduced, but when it comes to simulate the externally forced climate change, when I'm pushing the models to warm, they are running too warm, really. And that would mean that the projected warming into the future, likely, under this point of view, will be also exaggerated. Right? These are the 2 points of view. I have shown you both, and I will tell you which one I think is right. You have to decide by yourself, or wait 50 years. Now let's have a look at other variables. Trend in other variables simulated also by climate models compared to observations. And for you that may be working in the Arctic environment or the Antarctic environment, this is the sea ice extent observed in the Arctic. Sorry, the title is here, cannot be seen. This is the Antarctic sea ice extent. And I think this is the minimum. So the February, this will be the September sea ice extent. The observations are the black line. And we see, of course, a very strong negative trend in sea ice cover. You have heard that, right? Okay. What do the models are producing? Well, first of all, an incredibly high range in the mean sea ice extent. So some models are producing 12 million square kilometers, some models half of it. That's really, half of it, driven by the same forcing and the same physical equations. I won't say much. But the trend that is produced by the models, and do you have the histogram? No, I don't have the histograms here. But, I will tell you that the trends are too weak compared to observations. Here we have the opposite situation. The observations of sea ice cover are indicating a very rapid warming of the Arctic, and the models do not reproduce that. So no model can reproduce this very strong trend in sea ice retreat in September. On the other hand, if we go to Antarctica, we have in the observations a positive trend. So the sea ice extent in Antarctica is increasing. You have heard that also, right? And the models are all producing a reduction. All of them. Here the sign is wrong in all models. There are some explanations for this. So here you can see also the trend in the observations and the mean. This deficiency can be related to the ozone-induced atmospheric dynamics, which for Antarctica is very, very important. So the stronger winds around Antarctica that blow the ice toward the north, that more ice can be formed. If that process is not really replicated in the models, then you get a wrong result. But again, let's look at the range of simulated sea ice cover of Antarctica. Some models also produce 0, almost, and some models something like 15 million square kilometers. If you are again working in climate impacts into the Arctic, you have to be very aware what model are you using, what is the mean sea ice cover produced by the models, if that's important for you or not. Probably yes. Now let's have a look at, as mentioned before, a phenomenon, the paramount phenomenon of internal variations, which is the ENSO, El Niño, La Niña Southern Oscillation. I will just give you a very quick reminder because I assume that you have heard about it as well. So this is a series of the so-called ENSO index or SOI index. It is based, difference in the sea level pressure between Darwin, which is a station in Australia, and Tahiti in the Eastern Pacific. But you could also think about a measure of sea surface temperature off the coast of Peru. It's just the sign will be the opposite. And you can see that you have events actually. Yeah? In some years, for instance, in 1982, we had a very, very strong warming in the of the Peruvian coast, one of the strongest ENSO events. But otherwise, well, the temperature is well relatively stable, but we have sudden events. And the reason is a coupled mechanism between the atmosphere and the ocean. So what is this? A cross section of the Pacific Ocean. We have here Australia and South America. We have the trade winds, are blowing from the east to the west, and that's the winds that well, the Spaniards and the Portuguese used to travel to South America and then to the Philippines from South America. And these winds are producing an upwelling here in Peru, so upwelling colder temperatures, so the water is here really cold and here is warm. We have also a sloping sea level, so a difference of sea level because of these different temperatures of about 2 meters, something like that, between the west and the east, and the sloping thermocline in the ocean. So sometimes, for some reason, the winds get weaker, the trade winds just stopped. For some reason, from some stochastic variations that cannot be really predicted. Well, that produces that the upwelling stops suddenly. The waters warm here very rapidly, here in the Eastern Pacific, and they cool here. And this is associated also with a change in the convection here in over Indonesia and subsidence over South America. So the world circulation gets weaker as well. And we have then a sudden warming. This is accompanied by worldwide climate anomalies. This is a very, very large area, right? So the tropics, so the area between 30 north and 30 south is half of the Earth's surface. And the Pacific Ocean is a very big ocean, so this is a very, very large proportion of the Earth's surface. And this ENSO index, ENSO changes of variability can be seen in all the global variables. Even the CO2 concentration in the atmosphere changes. But also maybe the climate in Europe, and of course the climate over North America. Okay, the timing of the ENSO, yeah?
But why is that in North America? Is that on the east side? There is the cool part, and then there is that.
Well, I mean, normally you have here very heavy precipitation. When an ENSO event kicks in, becomes here very dry. So the atmosphere is not warm anymore by this precipitation. And that triggers a wave train over the whole, western hemisphere, in the northern hemisphere. So a series of lows and highs, and that modulates the climate over North America. That calls the Pacific North American pattern, it's called. But sometimes for very strong events, and actually for this year a very strong event is predicted and seems to be on the way, the climate over Europe will be also affected. So be prepared. If a very big ENSO event happens, then the global temperatures will go up very considerably. So we'll probably have a record year if that happens. However, last year, in May, we had also a prediction of a very strong ENSO event, and it didn't happen. So that means that we are not really able to predict the occurrence of ENSO events even with 3-4 months in advance. It's like, in weather prediction, we have a limited predictability of 5-6 days at most. In climate, in seasonal climate prediction, to a summary, it's a mess. It's not working. There are many groups working on seasonal prediction. Also some groups working on decadal climate prediction, but it's really not working. So the skill is almost zero. So it may happen that the ENSO event this year will not happen, although all predictions are indicating that it will be a very strong. So it will be a good test for the models. So you can perhaps be aware of the news by, if an ENSO event occurs, it will be by December. So you will have it all over the news in the papers. Okay, so we saw in the index that this ENSO events happen irregularly every 4, 5, 6 years. But it's not an oscillation. You cannot say if it happened last year, then it will be in 5 years' time. It's an irregular oscillation, an event that happens in the mean every 5 years. What are the models producing? Here I show you what is called a spectrum of the sea surface temperature in the Pacific. So it's something that gives you to what frequency or to what periods this time series of temperature is oscillating, which is the main period. Here are the black line. It's not very well seen, but the black line are the observations. And as I showed you, the peak is about 5 years. So here you have 2, 7 years. So every 5 years in the mean we have here is the set of older models. Here is the more modern models. In the older models we have actually some models that produced like a clockwork. Every 3 years an ENSO event. And you can predict it very well. So it was very, very unrealistic. Some models did not produce any ENSO event at all. So it was completely out of the question that those models could simulate something like an ENSO event, which is the main pattern of internal variability. If you can imagine that we live on Mars, on outer planet, and we will be monitoring the temperature of the Earth, we will see that every 5 years, or every 3, 4, 5 years, the temperature is blipping, like a bulb. We will see it. And some models will not produce that at all. If we go to more recent models, well, they look a little bit better, closer to the observations, but there are even still models that produce an ENSO event every 2 years, very regularly. And one of those is the German model, the ECAM model that is run at the Max Planck Institute. You can see it in the observations every 2 years. You have exactly an ENSO event. So this is completely unrealistic. Now the question is this model able to simulate properly climate change in the Pacific? Well, it's an open question. I mean, maybe yes, maybe no, but there is an uncertainty there. And well, in the last 5 minutes or so, I will try to show you now a mixture between climate change projections and internal variability. So we have seen at the first part of the talk what the climate change, so the externally forced climate change. Now we have a look at the internal variations. Now we merge all together. We know that in the future, when climate changes, we'll have both at the same time. We have climate change caused by CO2 increase, but also we have these random variations that are unpredictable. And we don't know that it will be a decadal time scale or centennial time scale, but there will be something. And we don't know also the amplitude. How big are these internal variations in the future? What can we do to estimate that, or to have a range of uncertainties? Well, the method actually is to produce many, many simulations with exactly the same model, so that we don't have any changes in the model structure. It's the same model exactly, and the same external forcing. But at the beginning, we change just the initial conditions. So to have twin simulations. Instead of 2, we have 50, for instance, or 40. They are all driven by the same forcing, but the initial conditions at the beginning are slightly different, so that they get out of sync and they produce all the different internal variations. And this has been done in one institute in America, in NCAR. So they run 40 simulations exactly with the same model, exactly with the same scenario for the future, and they looked at the temperature change simulated by those models over North America, right? And, well, surprise, surprise, if you look at the mean of all simulations, you have a stronger warming at high latitudes, or the polar amplification. It's a very well-known phenomenon. But there were one simulation that produced a very, very strong warming, so up to 6 degrees in some areas, and one simulation that produced very, very little warming, even with cooling in the center of the United States. This simulation and this simulation have the same rights. Both of them are exactly possible. We cannot say this is more likely or this is more likely. They are all driven by the same external forcing.
What's the difference of the initial condition?
Well, they are chosen at random. The simulations are started in, you see, 1910. So nobody knows what the initial conditions were in 1910. We have few observations, but the model would need a complete description of the ocean and the atmosphere. Nobody knows that. So they are produced, well, you have to guess what will be the mean climate at that time, and then you produce random fluctuations to produce 40 simulations, all different. For instance, this is for the globe. So if you average of the whole globe, all simulations tend to produce very similar warming because these random fluctuations average out, right? But if you go to the United States, so smaller scales, or Seattle, or well, Phoenix, so to local conditions. In Seattle, for instance, you have one simulation that goes up 2 degrees until 2050 only. So it will go to 4 degrees at the end of the century. And one simulation is completely flat, or even cooling. So that gives you an idea about the enormous range of uncertainty when you try to simulate the local temperature. Temperature is a well-behaved parameter, and very important parameter. If you look at local details, assuming that this ensemble simulation is correct, so the model is perfect, assuming that the model is perfect, there are no mistakes in the model, you cannot say if in Seattle the temperature will go up by 2 degrees or it will cool, right? Now, for precipitation, the same story, even worse, actually. You have also the mean of all simulations. You have, well, higher precipitation in the north, drier in the southern United States, right? So you can see, okay, look, the models are producing the drier in California, the dryness that we are seeing now. This is, of course, a climate change signal, right? Now you look at one of the simulations and, well, it's producing a very, very strong drying in California. But you look at the weather simulation, it's actually precipitation is increasing here. And this simulation and these simulations have the same right, at the same level. We don't know which one will, both are right, actually, both are right. But we don't know which random fluctuation will be realized into the future. It's like playing lottery. We have the climate change, the deterministic, externally forced climate change, but on top of that, we have to buy a lottery ticket. And we don't know if we will win this one or win this one.
I have a question. Are those models also starting with the same initial conditions?
No, they are different. They are to produce this internal variability. So the initial conditions are randomly chosen. Okay, I think we have still 5 minutes and we don't have time for our exercise, right? So I thought that I will not show you this, and I thought that perhaps some volunteer will read out summary of one of the papers. What do you think about that? So to be able to summarize a paper in even less than half a page, even one paragraph for you alone, so that you are actually bound to still the main message, 2, 3, 4 sentences. And well, probably now for this occasion was you didn't have much time, but for the future, it's a very good exercise to learn how to write and to summarize. So what I would suggest you is anyone that wants to do it, the exercise still, you can send me per email and you get a feedback. If you are not interested or you don't want to, then of course I will not phone you. But I think it's a good opportunity. Well, you have to learn that. It's like the writing of the proposal. And if you do it many times, at the beginning, of course, as I did myself, the beginning was a catastrophe. So my first paper was awful. The second awful, and the last one a little bit less awful. But you have to really to practice writing. This is a very, very important thing. You can be a very brilliant scientist. You are all very brilliant, have no doubt. But writing is extremely, extremely important. Writing well is very, very important for your career. It can make the difference. These random variations. You may be very intelligent, very brilliant, but these random variations between a paper that is accepted, a proposal that is accepted or rejected, and a very important factor is how it is written, how it is summarized, how it is structured, makes the whole difference. Can make the whole difference. So I strongly suggest you to practice that a lot. And as I said, if anyone wants to send me those summaries, you will get my feedback, which is also not correct, it's subjective, but you will get at least my feedback. Then I will want to finish with one summary slide. Yeah, this is one of the questions that the paper, one of the papers, posed. Can we trust climate models? And that question can be translated as this one: is the Newton's theory of gravitation reliable? Right? We all learn that apples fall in school, and the moon and the earth attract each other. So it is reliable, right? And these workers working in, I think it's Chicago in 1920, they are absolutely sure that the theory of gravitation is reliable. Nobody will doubt that. However, if we step forward 100 years, or almost 100 years, and we ask an engineer that is working on GPS technology, they will tell you, Newton's theory of gravitation is useless for me. Because if I want to have an accuracy of, let's say, 2 meters, as I need for GPS, I need to include the general theory of relativity to correct the GPS. So for him, the Newton's theory of gravitation is wrong. So what is the message for climate models? Are the climate models reliable? Can we trust them? Well, depends what the model is written for, what I expect for the model. In this case, the theory is reliable because I only want to know if I'm going to fall or not. So if for a climate model I'm just asking it, it will get warm or cool on the global scale, well, maybe useful. If I want to know from the climate model if it's going to rain in Asco in 2050 more than today, probably not. So the question is, are the climate models reliable? Requires a subjective answer. Depends on your point of view and depends on your need. And to finalize then, in the debate of climate change usually, you have two opposing poles, not the north and the south, but you have some people that say everything is absolutely certain or everything is rubbish, absolutely uncertain. This is not correct, that stance. The real thing, or the more realistic position, is that we have shades, well, not 50 shades of grey, but, but a few. So there are some things that are very uncertain still. There are other things that are very certain, as I said at the beginning. For instance, that CO2 concentration must lead to surface warming, and will lead to surface warming. But other things, as we have said, are much more uncertain. And we cannot lump them all together. We have to be discriminative and see what are the strengths and what are the weaknesses of all models. Okay, now let's go for a coffee break, I think, right?
Well, let's first thank you very much.
Well, thank you.